recording the session from here on. Okay, so there is something that the toolbox that we had for the computing limits. One of the cases was the quotient law. So if you have two functions, each one of them have a limit, but when you try to compute the quotient, you can see that while the limit of the denominator is non-zero, and you can just go ahead and do the quotient law, meaning that find the limit of the numerator and limit of the denominator and divide them. So this is only true when limit of the denominator is not equal to zero. Very nice. Now we go ahead and try to see what happens if limit of the denominator is actually zero. For these cases, for this case, there will be two different scenarios. When the limit of the denominator is zero, first thing it has to say is that the quotient law cannot be applied. But then you need to check the numerator. When the limit of the numerator, which we assume exists, and it is a number not equal to zero, and the other scenario is that the limit of the denominator, which we assume exists, is equal to zero. Very nice. So you have these three cases. These are the only possibilities if f and g, their limit exists. Well, we already covered this part. What about if you have limit of numerator non-zero, but limit of the denominator zero? This will give us a non-existent limit for the quotient. This will be does not exist. But it's a special kind of does not exist, meaning that this limit is actually infinite limit. So it means that as we get closer to a, this non-zero number over the limit zero, this whole quotient will grow either big and big positive numbers or very negative, big negative numbers. That finishes there and done. We actually covered this one in week 4, and we will do more reviews for the next week there. What about the case that the denominator is also zero? So in this case, numerator and denominator, that they have limit zero. This is when we say that we have 0 over 0 in determinate form. 0 over 0 is not a value. It is just a form that says that I have nothing to say at this point. You have to do more things. And for the cases that at least we have rational functions, or in other words, you have numerator polynomial, denominator polynomial, we do these 3 steps to resolve this indeterminate form. It is factor it, cancel it, is what we say, and then take the limit again. When you have 0 over 0 or limit of a polynomial equal to 0, you will find, if you try to factor that polynomial, you will find the factor of x minus a. This x minus a, I'll call it vanishing factor. So you factor out vanishing factor from both denominator and numerator. And then since it was 0 over 0, both of them will have some powers of vanishing factor. You cancel them and you get a new limit and you try to solve it. The focus for today will be doing some examples for these cases. Before I continue, is there any questions, any comments? Very good. So I will go ahead and do the first example here. Okay, so this is a polynomial over polynomial rational function. We always start with the denominator. And using limit laws, I can see that this is 0 cubed plus 4 times 0 squared minus 0. This is 0. The denominator has limit 0. Well, then next step is go ahead and find limit of the numerator as x goes to 0. So this is again limit laws. And that will give us 0 squared minus 3 times 0, which is again 0. So what we find here is 0 over 0. I cannot write 0 over 0 here. 0 over 0 is not a number. It is just a form that tells us you have to do more things to be able to evaluate that limit. What is the more thing that we have to do? We find the vanishing factor both in numerator and the denominator. Here, x minus 0. As x goes to a, the vanishing factor is x minus a. In this case, x minus 0, which is just x. Okay, let me just factor these guys here. So I can factor out that. And there will be definitely such a thing. Here I do x squared plus 4x minus 1 as x goes to 0. So the vanishing factors are out there and I can cancel them. And this will give me a new limit, which is again a rational function. And when you have rational functions, a limit of rational functions, you always start from one thing. Hope that the quotient law will work. In other words, you try to check that the limit of the denominator is non-zero. And let's see what is this case. Minus 1. And yes, it is non-zero. If limit of the denominator is non-zero, you can go and use quotient law, and that will give you limit of numerator over limit of the denominator as x goes to 0. And that is nothing but 0 minus 3, 0 squared plus 4 times 0 minus 1. And that is negative 3 over negative 1, which is just the number 3. Okay, so note, we started with a limit which ended up, it turns out that it's a 0 over 0 indeterminate form. We don't give up. We have to do some more work. What we do, we factor, we cancel in the case of rational functions. Here's how we factor. The vanishing factor here is x, so we factor x from numerator, from denominator, we cancel them. And then from this point on, we found a new limit. This is like, okay, someone has given you this limit here and asking you to find this limit. Okay, it's quotient. You hope that you can use quotient law. So go ahead, check the limit of the denominator. Is it 0 or not? If it is non-zero, which was the case for us, we do the quotient law and evaluate the law. Any questions, any comments before I move to the next example? Okay. Well, the same steps, limit of the denominator, first thing to check as x goes to 1, this is using limit laws. This is 1 plus 1 minus 2, which is 0. Then I cannot use quotient law. That's the result of that computation. I can go ahead now and find the limit of the numerator. 0 square minus 3 times 0 plus 2, and that is 2. Oh, sorry, I'm not finding the right limit. This is 1 squared minus 3 times 1 plus 2, which will be 0. So what we see is that, oh, this is 0 over 0 in determinate form. And now I have to do factor and cancel. Vanishing factor here is x minus 1. Well, these are quadratic. You try to factor them, and you will notice that both of them has minus 1. Two numbers add up to -3, multiplied to 2, -1, -2. Two numbers add up to 1, multiplied to with the product -2, that's plus 2, -1. And as you can see, this cancels with that, and we have completely new limit. It is again a rational function, so we make sure that see what is happening in the denominator when we take the limit. This is 3 not equal to 0, so I can use quotient law and go ahead and find limit of the numerator, limit of the denominator, and this is plus, and this is 1 minus 2 over 1 plus 2. This is -1 over 3. When we have 0 over 0, we may end up with existence limit, these two. I'm so sorry. So we can have two existent, either existent limit or does not exist limit. So 0 over 0 can end up to any of these cases. Let us do this other one here. Here, limit of the denominator, you go ahead and find that, and you see that, well, this is 0. So I don't do the details of this computation. This will be 0. And limit of the numerator, you will see, is again 0. We are in 0 over 0 case. And now we want to do something very similar to what we did in the previous examples. In the denominator, the vanishing factor is x minus 4. And when we, this is vanishing factor. When we try to find this, so x cubed minus 5x squared plus 4x. I factor out x, this will be x squared minus 5x plus 4, and that is x minus 4, x minus 1. That's the factorization, and it has the vanishing factor. But in the numerator, this is not a polynomial. This is one of the cases that is not polynomial, and you have to be able to do resolve these kind of indeterminate forms. The way it works is this: if you have root of something minus another thing, it could be root of something or anything else there, you can multiply this guy by what is called it's conjugate. Conjugate is when you, instead of plus, you put, instead of minus, you put plus there. You see, something minus another thing times something plus another thing. This will be the first one squared minus the second one squared. And that way, you can get rid of that square root there. In our case, the numerator is 2x plus 1. I want to write it as minus of a whole thing. That whole thing will be this, minus x minus 1. And its conjugate is root 2x plus 1 plus x minus 1. So what we do to be able to factor this guy, the vanishing factor in the numerator, we multiply the whole numerator and the denominator by the conjugate of this guy. Again, the reason that we did multiply by conjugate is that way we can get rid of that square root. And in the numerator, you will see that we have this part squared, which is 2x plus 1, minus the second part squared. So if you do this, you get 2x plus 1 minus x minus 1 squared, which is 2x plus 1 minus x squared minus 2x plus 1. And this is nothing but minus x squared plus 4x, and 1 minus 1 is 0. In the denominator, okay, I have the factorization here. I put it there. But remember that I also multiplied this guy down there. So I can write the whole thing, 2x plus 1 plus x minus 1. Okay, now this guy here, we saw that it's minus x squared plus 4x. And I can now factor this guy. Alexander, just give me a second and I will. This guy will be minus x. I factored this. This will be x minus 4 and x minus 4, x minus 1, 2x plus 1 plus x minus 1. Okay, then we have the vanishing factor. This guy cancels, and you can continue now from here. Do it yourself. I'll leave it there because now if you compute the limit of numerator, you will notice that it is not, the limit of denominator is not 0. So use a quotient law. Alexandra, yes, please.
I was just wondering why it, when you multiply by the conjugate, it goes from negative x plus 1 to plus, and then bracket x minus 1.
Oh, the conjugate itself you're talking about, or?
Yeah, like I was just because there's not a bracket around the minus x plus 1.
Oh, I see. The point is that I want to see this guy either plus something, or I want to see it as minus something. Doesn't matter. If I want to see it as plus something, you have to see it as minus x plus 1. Okay. If you want to take it as minus something, you have to factor out the minus sign from this whole remaining term, and that will make it x minus 1.
Okay, thank you.
Either way will work, and their conjugate will be just, if this is plus, this will be minus. If this is minus, it will be plus. But at the final result will be the same thing. Okay, any other questions, any other comments? Well, this example, very quick, limit of the denominator as x goes to -1 is 1 squared minus 2 plus 1 is equal to 0. Limit of the numerator as x goes to -1 is -1 squared minus 2 times -1 plus 1, which is 1 plus 2 plus 1, which is 4. So limit of numerator is not 0, limit of the denominator is 0. So this does not exist, and it is actually infinite limit. That's how you find that guy. So you can go into detail and try to figure out it is plus infinity or minus infinity, but you have to bring in one-sided limits. That's something that we will do a little bit next week, examples of that. The last example is for you to show that sometimes after resolving indeterminate form, we may end up with something which is some limit which does not exist. So here, if you do the work, complete the work yourself. Then you try to factor out. So the numerator already is x minus 1. X cubed minus 4x squared plus 4x. I can factor out x. This is x squared minus 4x plus 4. And this is complete square, actually. X minus 2 squared is there. So it's x minus 2 squared as x goes to 2. Now, when I'm trying to cancel, I can cancel one of these with this guy here. And then the remaining is actually 1 over x minus 2 as x goes to 2. And when you look at this guy, limit of the denominator as x goes to 2 is 0, and limit of numerator is 1. So this does not exist. And actually, you can say a little bit more. When x goes to 2 from the negative side, the limit is minus infinity. And when x goes to 2 from the positive side, this is plus infinity. Does not exist. It's infinite limit. We specifically can say what is the value, or when is positive infinity, when it is negative infinity. Any questions, any comments there? Okay, I have one more example here. I will give you 1 minute or maybe a little bit more. Try to complete this example yourself. So try to see, it's multiple choice. Find the answer and then tell me what is which option you would choose for this one. Go ahead and you have 1 minute to complete this question. Do it, please. Please do it right now here. See how far you can go into this example. So I assume that you're doing the problem. And then when you find the answers, please send it on the chat so that I can see. 1 minute's almost done. Anyone has the answer for me there? Okay, let us see what would we do if this problem is given. The first thing, note that limit of the numerator and limit of the denominator exist. Both of them exist. So we are good. The reason that the limit of numerator works is because the assumption is given there. But limit of the numerator, as we do always when we have a rational function or a quotient, is that we find the limit of the denominator and it is 0. Now, we know that limit of the denominator is 0, so the limit of numerator cannot be, we cannot use the quotient law. And there will be two scenarios. If the limit of the numerator as x goes to 2 is not equal to 0, or limit of the numerator is actually 0. But look, if the limit of the numerator is not 0, then we will have a limit of the whole function. Since the limit of the numerator is non-zero, limit of the denominator is 0, this won't exist. There won't be, that limit is non-existence limit. But we know that the limit exists and it's equal to the number e. So this could not be the case. Definitely, the limit of numerator must be equal to 0 so that we get into the 0/0 case and indeterminate form. And then someone has resolved it in some ways and found the value of that. But this is now enough for us. Just by knowing that the only possible scenario here is that the limit of numerator is 0, I can go ahead and apply limit laws and get 2 limit of f of x as x goes to 2 plus pi must be equal to 0. And this is something that we are looking for, aren't we? So that means that I have to solve this guy for that limit. And this will be limit of f of x as x goes to 2 is minus pi over 2. And that way we know that, oh, this is the good answer for us. Any questions, any comments here? Just make sure that you understand this argument here, and you will be able to apply it in similar situations. Any questions, any comments? Is everyone out there? I cannot hear anything. It's as if there's no one there listening to me even.
Makes sense.
Okay, good. Thank you. That's nice. Yeah, please. You're not telling me any jokes. At least just say yes, no at some point. Ask me questions. Don't make me feel alone here. Okay. Then the next topic, I'll move to the next topic. This is about continuity. Continuity is a condition that is stronger than having limit. Here, the definition, just very quick recall definition. Limit a function f is continuous at a point A. Well, we are here assuming that function f is defined around A. If this happens, that limit of the function as x goes to A exists, the function is defined at A, and you can find its value. Continuity means that these two guys are the same thing. Finding limit and evaluating function are the same thing when the function is continuous. And you see, without continuity, there is no reason that value of function is equal to the limit. This is a stronger condition than just having limit. Well, as a result of this guy, just definition, being able to apply limit laws, all polynomials and rational functions are continuous on their domain. That's why when P is a polynomial, you learn that limit of P of x as x goes to A by applying limit laws. This is the same thing as evaluating. Now you can say either using the limit laws or from this point on as a reason for this equality, you can write polynomials are continuous. So that's a new thing for us. We have done enough work with the limit laws, and that will give us a little bit of space to freely walk around and find these values. Let's do some examples here using the graph. When I look at this graph, first of all, there are 2 points that I want to focus on. One is -1, one is 2. And I noticed that when I'm working at 2, f is defined at x equal to 2. It means that on the graph, there is a value for this guy. So actually, we know that f at 2 is about 0.5. I'm just writing approximate. The point is that that bullet, the solid bullet is there, and that means that it is defined. The second thing is that limit of this function as x approaches to A, 2 here. When I get closer, when I'm considering limit, I ignore completely the value of the function, and I see what happens to the values of the function as we get closer and closer to that point. And in this case, this is equal to 0. The limit exists, the value of the function is defined at that point, but limit is not equal to the value of the function at that point. So f is not continuous at this point, at 2. How about at -1? Well, f is defined at a -1. That's because just when you go over the graph, above x equal to -1, there is this solid bullet which shows me that f at -1 is actually 4. When I try to study the limit of this function as x goes to -1, I notice that, oh, there are two different ways. When I approach to x from the right, from the left of the function, from the left of x equal to -1, I follow this branch here, and it gets closer to -1. And this from the right, I'm following this branch, and it gets closer to 0. As a result of this computation, limit of f of x as x goes to -1 does not exist. The right limit and left limit are not the same. Since this does not exist, even though it is defined at that point, we can conclude that f is discontinuous. That's another wording we will use for not being continuous at x equal to -1. About every other point on this graph, when you have a graph of function, and when you walk on the graph, and you don't need to pick up your pen as you trace the graph, that means that your function is continuous at those points, actually on that interval. And here we can say that f is continuous on all points but just x equal to -1 and x equal to 2. Other than that, the graph shows that the function is good and continues for everything. Any questions? Any comments? So continuity means not only you check the limit, you check that the function is defined at that point, and also these two things are the same thing. Let us do one example here. This is a function, piecewise defined function. The first thing you notice is that for x is less than -1, the function is given by 2x plus a. 2x plus a, no matter what is the value of a, this is a polynomial. And it is continuous. So our function, which is equal to this polynomial on all x is less than -1, is continuous, no matter what is the value of that number x. For x's between -1 and 0, I am intentionally dropping the values of 0 and -1. The function is given by x squared plus 3 over x minus 1. Yes, but this is a rational function, and it is continuous on everywhere but 1. Yes, so this function is a rational function. It's continuous everywhere on its domain. Its domain is everything but number 1. That means that our function, which is only equal to this rational function on the interval -1 to 0, so f is continuous because that bad point is not included in this interval at which the function is equal to that rational function. So f is continuous on -1 and 0. The same argument will work for sine b sine x over x. So for x is bigger than 0, f of x is b sine x over x. And this is sine x is continuous, x is continuous. Their quotient will be continuous everywhere with this quotient is defined. So this is continuous on R but 0. But we don't need to be worried about 0 because at 0, our function is not using this formula. So upshot of all these work that I was talking about, like all these points, is that for f to be continuous on the whole real line, we only need to check its continuity on 2 points. X equal to -1 and x equal to 0. So I go ahead, f at -1 is defined, and actually it is defined by this formula. So it is -1 squared plus 3 over -1 minus 1. This is 4 over -2, it is 2. Limit of function as x goes to -1. At -1, well, if I approach from the left, it's given by function. If I approach to -1 from the right, it is given by another formula. So that means that I have to separate this and look into one-sided limits. One-sided limit for 2x plus a when x goes to -1 from the left. This is 2 times -1 plus a is a minus 2. From the right, this is but we have done this computation and we know that it is 2. Okay, now I have right limit, left limit, and the value of the function. Since I am interested in having a continuous function, it means that the limit exists. That means that a minus 2, the left limit, must be equal to 2, which is the right limit, and it must be equal to the value of the function at that point. Okay, so limit of function as x goes to -1 from the left must be equal to value of the function at -1 and must be equal to value of the function limit of the function as x goes to -1 from the right. That means that we have this equality, and that equality is nothing but a minus 2 equals to 2, which is an equation for 2, and it gives me that a must be equal to 4. Same kind of work can be done for x equal to 0. F at 0 is given by 0 squared plus 3 over 0 minus 1, which is 3 over -1, and that is -3. Limit of the function as x goes to 0. This is again piecewise defined function, and around 0, it has different values. Let me just do this, and then Adam, you can ask the question. Just give me a second here. So from the right-hand side, I have, okay, maybe I do the left-hand side first. I have x squared plus 3 over x minus 1. This will give me 0 squared plus 3 over 0 minus 1, which is -3. From the right, This is nothing but b times limit of sine x over x as x goes to 0. Well, this limit, we will actually, you have already studied week 4, and in week 4, using a squeeze theorem, we show that this limit is equal to 1. So I have b times 1. So continuity at x equal to 0 implies that -3, the value of the function, the left limit, the right limit must be equal. So that means that b must be -3. Yes, Adam. Yes, please go ahead.
Professor, is the limit from x to -1, x squared plus 3 over x minus 1, isn't it -2?
Wait a minute. Which one is this? Wow. Even the value is -2. Okay, yes. Okay. Yes, I have been making a mistake there. Thank you, Adam. I wish I had asked you earlier. Well, that changes the value of a to 0, actually. Yes, you're right. You're right. Thank you. Any other question? Oh, this was multiple choice, and now I have the correct answer. Yes, before with what we did, this could not be the correct answer. Okay, yes, below, yes, please.
Wait, so just to verify, you changed it from 2 to -2?
Yes, it was negative. I did make a mistake here. You see, this 4 over -2 is supposed to be -2. I just wrote 2.
Oh, okay.
Yeah, that was a mistake. Silly mistake there. Any other question? Any other comments? I think this covers the good portion of the continuity. There is one topic, IVT, intermediate value theorem, which is covered in week 4, and we will do examples for that next week, early next week. So just make sure that yeah, you do look at the content of week 4, and make sure that you're covering the values, the assignment problems which we have already done examples for. I will pause the video here.